So today we'll see the another approach to design the processor. Okay. So and what is the objective of this processor is that like we want to achieve the uh, processor performance, right, which would be better than the single cycle one and the multi-cycle one that we have seen, right? So in that way, the objective is to design a processor whose clock period would be smaller than single cycle one, or maybe at least equal to the or more than multi-cycle one, and the CPI would be 1. If you remember in the multi-cycle one, right, the CPI was more than 1, right? Okay, so that is the objective. Okay, so now first we will see the disadvantage, or we will compare these two other two approaches to design the processor. So one is single cycle one, other one is the multi-cycle one, right? If you remember, we solved this problem, right? Now you see, to execute the program which has this many number of instruction, right? So it takes this amount of time. However, in this case, same program is running on multi-cycle processor, right? So here it is taking this amount of time, right? Sorry, this is for your clock period, right? This one is clock period, and here time is this one, and this is the time, right? And you can see here the CPI, right? CPI is 1 here, however, here CPI is more. Okay. So now we want to build a processor whose CPI would be 1, right? And the clock period would be lesser than the single cycle one, right? Okay. So now, so what was the problem for multi-cycle based processor, right? So what we did, we split the entire data path, right, into 5 steps, right? Based on like LW was the slowest instruction, right? And based on that, we split the data path into 5 steps, right? So in that way, if the T for single cycle is, let's say, TS, then we are splitting this by 5, right? So in that way, if you remember here, so this is the T. Now if we divide by 5, then it should be this one, right? But you see here, it is not happening. Okay. Okay, so that was the problem. And also, and I mean, so if you remember the clock period calculation for multi-cycle one, right? So each, we are taking the max of all the source and destination pair, right? And then the maximum one is deciding the clock period, right? So in that way, it is saying that each step takes unequal length of time, right? Got it? And also, if you remember in the multi-cycle one, right? So only one stage is busy, and the rest of the 4 stages are sitting idle, right? So that is also a disadvantage, right? And also we have incorporated, like in the multi-cycle one, so 5 non-architectural register and the multiplexer, right? Got it? So so I mean, if we remember the single cycle one, right? So if you remember, we have I mean more FUs, right? Right, that means we are not sharing the FUs. Like if you remember the multi-cycle one, right, the PC's address calculation, right, PC plus 4 we are doing using the ALU, right? So that is what sharing, right? And here CPI, I mean for single cycle one, CPI is 1, and another term is called the IPC. IPC is nothing but instruction per cycle, right? So it is nothing but 1 by, I mean 1 over CPI. That is the IPC, right? So here in this case, so it is 1. And clock period, so let's say T single, right? Now in the multi-cycle one, the FUs are shared, right? Got it? And here CPI is more than 1 and IPC is less than 1. Got it? So we have seen, right? So in the earlier example, average CPI is 4 point something, right? Got it? And here clock period is, you see, it is lesser than the single cycle one, right? Got it? So here also, like in this class, we have discussed around, I mean, six instructions, right? Now you see their clock cycle time, right? I mean, CPI, right? You see here single cycle is taking only 1 cycle, right? However, here it is taking 5 clock cycle. Got it? And here CPI is more. Here CPI is only 1, right? Now the objective is we want to design a processor whose CPI would be 1, like single cycle 1, and the clock period would be lesser than the single cycle 1, right? So how can we do that? Okay, so before going to that, so I mean, you see this is the data path of the multi-cycle processor, right? So here you can see this is our IR register, this is MDR register, right? So this is the fetch stage, right? So when instruction is in this stage, then these stages are sitting idle, right? So this decoding stage, right? EX stage, right? Then memory, right? Or write back. Got it? So these stages are sitting idle. We want to use these stages. Like when some instruction is, I mean, here in the phase stage, then we also want to use these stages for other instruction. Okay. So can we use, I mean, can we perform that operation? Like, okay. So how can we do that? So what do you mean by pipelining? Okay. So before that, like let's say this is one example, okay, of a chemical plant. Here you can see this is the input side and this is your output side. Okay. So in this input side, you see water is coming, and this one is the pipeline. Okay. So water is flowing through this pipe, and you see first we are cleaning that water. Okay, using this filter. Okay. In the next stage, you see we are adding some materials with the water, right? And that we are saying that. So this stage we are saying filter, and this stage we are saying that mixture, like we are mixing some additive with the water, right? And then here we are heating up that water, right? I mean, mixed water, and then it is coming out as a steam as a output. Got it? So I mean, using this I mean example, or I mean this example, I mean we can use this example to build the processor. Got it? Got it? Or do you have some doubt? Why? I mean, if you remember also, like, right, when we first developed the medicine, right, we do experiment with the rats, mice, right, and then we apply that medicine to ourselves. So you see, we take something from nature for our use, right? So same way, here also you can see this example. I mean, we can borrow some information from this, and we can apply it into the processor design concept, right? So this kind of reasoning is called the analogical reasoning or parallel reasoning, right? So here you can see here. So in the earlier case, we have 3 stages, right? And here the stages are filter, mixture, and boiler, right? Now let's say if we say this is our source domain. Source domain means we know this example, right? We apply this information to design the processor. So that is our target domain, right? So here you can see we have 3 stages. Okay. So in this processor, we have considered only 3 stages. Fetch, that is the stage 1, and then decode. Here, I mean, in the stage 1, we are fetching the instruction. in the second stage, that is the instruction decoding stage, we are decoding the instruction and then we are executing the instruction here, right? And here you can see instruction or memory word are coming as a input, and here this is the output side. Got it? Now if we perform the parallel reasoning with this, right? So here this water is nothing but our instruction, right? Okay, and here the steam is nothing but our output that we want to, like, right, execution of this instruction, right? I mean, after that we'll get the output here. Got it? So in that way, you see here, like we have 3 stages, and this is the, I mean, this x-axis is the time axis, right? So first time stage 1 is used here, you can see, and the next time, right? So the first instruction, let's say this is the first instruction. Okay, now first instruction using the second stage here, and then we are fetching the, got it? So here, so let's say this is the IF stage, and then decode stage and EX stage. So the we are fetching the first instruction here, and then it is moving to the second stage, it is decoding, and then we are fetching the second instruction here, right? So in this way, here you can see all the stages are busy, right? So we have 3 stages. So in this stage we are fetching the third instruction, and then here we are decoding the second instruction, and here we are executing the first instruction, and then it finishes the execution, right? Got it? So so what is the difference between these two domains? So this is our target domain, right? Got it? What is the difference between the source and target domain? Like, so you see, right? So water is continuously flowing. We are not holding them, right? Right. And here, in this case, this is we are holding them, right? So that is the continuous one, and this is the discrete one. Got it? So now, okay. So this is the idea. Okay. So now we'll see the general principle to design the pipeline processor. Got it? So here, like you can take, here we are discussing about the MIPS processor, but let's say, in the previous classes, right, we have covered the min-max processor also, right? So you take any function, let's say any C function or any mathematical function, right? And then we can split that function into smaller sub-function, right? And to, design this pipeline processor, right? So first, let's say we have function f, and we can split it into, let's say, different sub-functions, right? Okay. Now here, like when, so this function, right? When we realize this function means it can be like your variables, right? Or some FUs, right? So when we design this function, then the component that required for design this function is called the stage. Okay, got it? Hardware, right? To develop this small function is called the stage. Okay. Now then this is the first stage, let's say stage 1. Now this is the stage 2. Now this is the stage 3. Okay. So now this point is saying that the input to the sub function is totally comes from the output of the previous sub function. So in this case, let's say this is the second sub function or stage, right? So all the input would come from this stage only. But we'll see also that input will come from this previous, from here also. So that will create problem, but it is expected that input should come from the previous stages. Okay. So we'll see, like if we take the feedback from this, it will create the hazard that we'll discuss. Right? But it is expected that if it has this kind of thing, then it is very good. Okay. And other than input and output, there are no interrelation between the sub-function. Got it? And that we have discussed, like, so function means like right? Any small C function you can, right? And then if we design that function using some hardware, then we are calling them as stage. Okay. And now, so we have to design this stage in such a way that each stage take, I mean, almost equal amount of time, because that will decide our clock period. Right? So this is the general principle. Okay. Now we'll apply this principle into MIPS processor, pipeline-based MIPS processor, right? So here you can see we have, I mean, when we discuss the von Neumann model, right? So we have discussed these 5 stages, right? And here, other thing is that, like, first we have to find out the delay component, right? I mean, delay component means here we are saying that each stage would take almost equal amount of time. Right? Now here we have 5 such stages. So here we have fetch stage. So fetch stage means it includes one, will fetch the instruction from memory. Okay, and then we'll decode it, and after that we have the reading operation, right? To read the register, I mean content, right? And then we have the execute stage. We have the ALU there and memory, right? So for store or LW, right, we'll use the memory, and then we have the write back. So these are the 5 stages. Now we have to distribute the component that we just discussed, right, memory, right, in such a way that they took exact, I mean not exact, almost equal amount of time. So now, so let's see this different component, right? So you see in the phase stage, right, we need the memory, right? And you see this is 250 picosecond. Right? Similarly, register file, you can see it takes this amount of time, right? Okay, so here, I mean, we have considered that the technology is, I mean, right? So 65 nanometer, right? That we have discussed in previous classes, right? Okay, and based on that, we have designed these components, right? Memory we have already there. Okay, and register file is also there, right? Now we want to distribute them in such a way that each stage can take almost equal amount of time. Got it? Hmm? So okay, so now we'll compare the timing diagram. Like, okay, so if we take those components that we just saw, right? Now if we take this component and if we build the single cycle data path, then what could be the delay, right? So phase time you can see here. So memory read operation, right? It is taking 250 picosecond. Right? Next, the decoding, right? And you see 150, right? So in this way, you see this is the end of one instruction execution, right? So it takes 950. And if you remember in the third slide, the T was 950. Okay, so this is for single cycle one. And next, you see we are fetching the next instruction after 950. Okay, so now this is the, like, I mean, this is the abstract view of the pipeline processor. You can see here. So we are fetching the first instruction. Also, it is taking 250 picosecond. Got it? And after that, you see we are reading, and also, I mean, after that we are decoding that, right? You can see here nothing is happening, that we will discuss. But here we are reading, okay, the value from the register file, right? So that is also 150, if you remember in this table. Got it? So 150 and, right? Okay, so we'll discuss why this is empty. Okay, and then here also, after that we are executing the instruction, right? And ALU takes so that empty part is, right? Got it? So we'll discuss, right? And then another memory, it takes 250, and then writing to the register file, that you can see here 100, right? Okay, so similar way you can see here after 250 picosecond, right? We are fetching the next instruction here, right? Got it. So in this way we are fetching the instruction. Right? Those components are not considered. Let's say we'll consider, but definitely we have to consider. But let's say this is very beginning, right? So, okay, so let's say we have already considered those things, right? Okay, so in this way you can see, I mean, this is the timing diagram, right? So here the distinction is that here we are fetching the next instruction for single cycle, right? After 950 picosecond. However, in pipeline, you see, we are fetching the instruction after 250. Why 250? Because I think, right, each we have to calculate the time for each stage, and then the stage having the maximum delay would decide the clock period. And here, right, memory is taking 250 picosecond, and because of that, T is here 250. And you see here, so 250 is the T, and then this recording part is taking. So here, register file reading is taking 150, then right, you minus it, then that period is sitting idle. Similarly for ALU, okay. So 250 and then how much? 200, got it. So this is the, I mean, you can say like fragmentation, like I think you know in OS, right? Okay, so same way, I mean, these stages are, I mean, a few times these components are sitting idle, okay, and that is happening because of unequal delay of each component. Okay, so this is the timing diagram, right? So now here, I mean, if we see the, I mean, performance, right? So here the clock period is 950 picosecond that we just saw, and here the clock period is 250 picosecond, right? Now throughput here, I mean, we are defining one term is called throughput. Throughput is nothing but output per unit time, right? So that means here output is like how many instructions are executing per unit time, right? So here throughput is one instruction per this, right? Because each instruction is taking 950 picosecond. Okay, so if we divide this, so right, this would be, I mean, this billion instruction would be executed per second. However, here you see, right? So 4 times, right? It is 4 times more, right? Got it? So in this way, it improves the performance. Got it? So here, I mean, same thing. Okay, here you can see how are the, I mean, resources, how are the resources are utilizing here, right? So at 5th stage, you can see here, all the components are busy, right? Got it? So, okay. Now, so we want to build the data path for pipeline processor, right? So here also we have 5 stages, right? Now in each stage that we have discussed, right, we'll distribute the component, right, in such a way that each stage will take almost equal amount of time. So here, I mean, from the table you can see, right, these are the time consuming unit, right? So memory takes here 250 picosecond. Register file, I mean, read is taking 150 picosecond, right? ALU is taking 200 picosecond, right? And data memory is taking 200 picosecond. Okay, and these are the stages. Okay, I mean, sorry, these are the stage register. These are the stages. Okay. Okay, and this is the stage register. Okay, so now we'll take this instruction that is R type. Okay, so this is the format, I think you know, right? So here we are following the MIPS ISA. Okay, so here also it is 32-bit processor. Okay, instruction length is also 32-bit, right? Now this is our add instruction. We want to execute this instruction in this data path. Okay. So first what we have to do? We have to fetch the instruction. Then what is the step? So, right. So PC's content would come to the right. Okay. So this is the memory address, right? And then instruction would be available here, right? So if you remember, so in the multi-cycle approach, we had the IR register, right? So now we have, let's say that IR, right? We have inserted in this stage registers and we have given a name. This is IF and ID stage. Okay. So this is the actually stage register. Okay. So now if we fetch the instruction, right? So instruction has this many parts, right? So we want to store them here. Okay. So opcode and your RS field. What is the size of the RS field? 5-bit, right? RT and then RD, right? And also all these, right? Shift amount and then the right. So these are the registers. So here the size of the register, how many bits? 6-bit, right? Here also 6-bit. Got it? So all the registers are here. Okay. Now after this, what we have to do? We have to decode. So, so for decoding, like what is the purpose? I mean, through which we can decode this, right? So this opcode will go to the controller. Let's say we have here one controller. So it will go to the controller, right? And then we have to, right? It is add instruction. What we have to do? We have to read to value. So let's say this is our RA port, read address A, read address B. So got it, right? And the value would be available here. And let's say if we store them here, right? Same way, if you remember the multi-cycle approach, right? So here, let's say we are giving the name as like, okay. And let's say here, got it. So okay. And then what we have to do? So then what we have in the ALU, I mean, we have to generate ALU control, right? Right. And what could be the input here? ALU op. Okay. And then ALU control also takes func field, right? Then what we have to do? So we have func field here, right? But in this stage register, we don't have the func field. So what we have to do? Right? We have to create the space for func field, right? Got it. And then like the connection would be like this. It would come via here, right?
We can't directly forward it from this.
No. That is what we want to split, right? The entire stage, right? Into 5 parts. Okay. Got it. So then we'll add this value, right? and the value would be available here, right? Now question is, I mean, see, if value is available here, we can directly give it to from here, right? Right? So what do you think? Can we give it to from here? Hmm? Why? So you are saying no. Why? Right? Got it. Because this part is purely combinational one ALU, right? If there is a change in the input, right? I mean, next, because it is pipeline one, and in this data path we have more than one instruction, right? Then immediately that value would be changed here, right? So because of that, we have to first send this data to the register so that it can stabilize, right? Got it? So here, let's say LU output, right? Got it? So now let's say this is our write data. Okay. So now we can connect it, right, from here to our register file. So got it? Now how about the write register address? So that is which field would be that? RD, right? Now question is that can we give it from IFID stage? Anisa, what do you think? Why? Because add is here, right? And it is pipeline one. Some other instruction is here, right? It's not it. Then what we have to do? Right? So bring the RT here, sorry, RD, and it will go like hop by hop, right? And then we have to also allocate the RD here. Got it? Right? And now let's say that is okay. Clear? Okay. Okay. So now okay. So now how about like here you can see in this data path, right? We are not incrementing the PC, right? What do you think? Where should we I mean do that, like PC plus 4? Fetch or decode or EX or here? Why? Right? So we want to fetch the next instruction. So we have to place that circuitry, right, in the fetch stage itself, right? So let's say we want to add. Okay. PC and then 4. Got it? Okay.
This is performed by adder.
Yes, adder. Then what will happen if you want to perform this? What do you think? Is it a multi-cycle one or? Yes, but this is not the multi-cycle one. Now, if you if you like now, did you understand his question? He's saying that in the multi-cycle approach, right? We did this PC plus 4 using ALU, right? Now, if we perform that PC plus 4 through ALU, what will happen? Right? We cannot fetch the next instruction, right? Because at least it should wait that, right? Got it? So we want to fetch the next instruction after that clock cycle, right? Right? So because of that, we should have the, this is also, I mean, we have seen this kind of circuit in the single cycle data path. Got it? So next instruction would be fetched. And because of that, we have this circuitry here. Clear? Hmm? Okay. Any doubt? So now, let's say we want to draw the data path for branch type instruction, right? So tell me the way, I mean, so first we want to fetch the instruction. Got it? And then instruction would be available here. Then all these things, opcode, right? RS, RT, right? And then we have offset. Okay. So let's say, I mean, if we, I mean, offset we can do that, but let's say we have RD also here. I mean, some value would be there. Okay, and that may be the part of the things, right? I will discuss. So shift amount. Okay, and then okay. Now what we'll do? So let's say we have some operation. We'll concatenate these three field, right? Then we'll get the offset. It's not it. Got it? So we'll concatenate all those three things, right? So let's say that is a concatenate operation, right? Right?
Also, offset is stored in D.
So see, we can directly store it, but we want to optimize at the same time. We have allocated RD as shift amount and func field earlier, right? Can you reuse them? Question is that we are using them, right? Got it? Hmm? Right? So we can store this 6-bit, we can store here, right? The last 6-bit here, right? And then 5-bit here, right? It's not it. And then we will concatenate them, right? And then we'll get the offset. Get the offset here. Now before that, we have to read the value. Right. So this is RA, RB. Now let's say we have RS data here. So what is the width of this field? Prothomes 32, right? Here 32. Same way we have. Okay. Right. And then we'll perform the operation, right? And then the ALU control, right? So ALU off. Okay. Then we have to also take the func field. Got it? Because this is ALU, I mean, so this is same circuit we are using, right? This is the ALU decoder, right? So that so separate thing will come now from here. Okay, got it? Clear? So in this case, see, this is BEQ type, right? Got it? So we have to perform the subtraction, right? And what could be the ALU of value in that case? 0, 1, right? Remember? Functional may not be used, right? But we have this connection earlier, right? So, okay, so now here we are comparing, then we should have a 0 flag, right? A 0 flag is here. Okay, so same way, we have to take the value after the stage register, right? Because this is purely combinational, right? There can be change, right? So here also we have to allocate 1 bit register, let's say 0. What could be the size here? Y32. This is a 0 flag.
The memory location is
This is which memory location? This is stage register.
every the size of this.
Why? You are mixing with register file. So you can see in the inside this stage register we are writing, right? What are they? Opcode. What is the size of the opcode? Then what is the field of this register? I mean, size of this register.
Using 6.
Huh? What? Why it should be fixed size? What is the size here? And then next one, 5.
We are only using 6 bits out of 32.
Why are you mixing with 32? 32 is coming from here. So we are taking out the parts, right? And we are storing it here.
Every location is variable.
Yeah, that depends on the like what field we want to store there, right? So in this case, we have 6-bit register. Then here, what could be the register size? This is the flag, right? So then, got it? So it would be, right? And then, right? Also from the ALU out is also coming, right? And for that purpose, here we have, what is the width of this register? Right? ALU out. Got it? Now we have to calculate the right branch address we have to calculate. Now how can we calculate that? So offset is available here, right? Then what we have to do? Right? So let's say we have sign extension unit here. So how many bit will it produce? Right? So we have to save here also 32 bit. Let's say that is AC also. Got it? After that, what we have to do? Right? So let's say we have this unit. Okay. And then we have to add it with PC plus 4, and PC plus 4 is not available. What we have to do? Right? So we have to calculate the PC plus 4, right? So let's say got it. So this is plus, right? Adder 4, right? And here we have to store the PC plus 4. Got it? Then what we have to do? We have to also reserve PC plus 4 here. Got it? Now PC plus 4 is available in this stage. Now we can perform addition. Okay, so it's a PC plus 4 and then got it. So now tell me what we have to do. If branch is false, right? We have to load PC plus 4. If it is true, what we have to do? Right, this, right? Branch address. Now where is our branch decision? So branch decision is here, right? It is coming via this register. Then branch address is coming from here. So what we have to do? Right, we have to store here, right? So let's say that is branch address. What could be the size of this branch address, Prathamesh? Got it? Okay. So now we have to tell, right? Because this will only happens only for the BQ type instruction, not other at all, right? So we have to, right? So 0 will come from here and it should be only for, got it? Now this signal is available here. Now PC will get two values. Then what circuitry do we need here? Multiplexer, right? So okay, let's say 0 and 1. If it is 0, then value would come from, got it? And what could be the select input here? Output of this AND gate. Okay. And now we have to provide the branch address, right? So branch address will come from this stage. Okay. Clear? Hmm?
And in this one, we will get to know whether if it's equal or not in fourth execution stage.
After the execution stage, I mean.
But before that only we might have fetched 2 or 3 instructions.
Yes, that we will discuss. Earlier case, if you remember, I told you, like, if there is a feedback, then that will create hazard. Now it will create hazard, right? You can see. Here, you are saying, what if we keep the PC here? Huh. So offset, here we are getting the offset. Offset is coming from the instruction. And branch address, if you remember, PC plus 4 and then the offset. I think you can revise that. PC plus 4, not PC. You can check with single cycle. Which PC has the offset? Offset, see. So here, let's say here, BQ was here. It is coming, right? It is also storing here. We are calculating the offset and then we are performing the extension and we are storing it here. The next time BQ is coming here, what happened? What is your worry? So BQ is here, right? In this stage, we are calculating the offset, right? And then we are performing the sign extension here in this stage only. When BQ is also there, then we are storing it here. Now BQ is moving to this stage to this stage. It's not it. Hmm. Hmm. Because PC plus 4 Tell me. Here also after phase stage, what is your worry? This is phase stage only, right? It's not it. Now the things have been flipped, upside down, right? I mean, here you see adder is here. Earlier case adder was here, but stage is same. Right? It's not it. Clear? I think Omkar, what happened? Yes, offset is here. Yes, so offset, you see, offset, we are getting the offset here when branch is here. Right? And then we are calculating the sign extension and we are storing it here, and also BQ is moving here in this stage. But what is the issue? That I would suggest you to go back and revise. PC plus 4 only. PC plus 4.